Okay, so so did you so last time we considered Carnot cycle. For an ideal gas, which is composed of an isothermal expansion, an adiabatic expansion, isothermal compression, and adiabatic compression. Okay, this is not quite straight, but it should have some. And we proved that the efficiency, which is the work done divided by the heat absorbed, so there is heat absorbed from a source at constant temperature, temperature T1, and it is released to another source at temperature T2. And the work done is the sum of the heat absorbed minus the heat which is conveyed to the source 2. But we keep the plus sign with the convention that when heat is released by the system, it's negative. And we found that this was 1 minus T2 over T1. Okay? You have to do the last final step. So did you do it at home? Does it work? Okay, so Carnot was right. Very good. Okay. So from this equation, since W is Q1 plus Q2, you can easily find the equation of Q1 divided by T1 plus Q2 divided by T2 is equal to 0. Okay? Now, there are several interesting things about the Carnot cycle which allow us to introduce a very important concept, the concept of entropy. Okay? The concept of entropy is very, very important, both in thermodynamics and in statistical mechanics. And in fact, it is the interpretation of entropy as a function of the number of microstates which are compatible with a given thermodynamic state, which actually leads to all of Boltzmann's elucubration about statistical mechanics and the birth of statistical mechanics. But let's do things properly. So let me read you the statement of the second law as postulated by Lord Kelvin. Okay? So it's the following. A transformation whose only final result is to transform into work heat extracted from a source which is at the same temperature throughout is impossible. Okay? So it is impossible to just take heat from one source at a constant temperature and transform it completely into work without anything else happening. Okay. So, for example, this is a postulate, okay? It's a law, it's not a theorem. We cannot prove it, okay? We just postulate it based on the fact that people have tried to do that for thousands of years, and they've not succeeded, okay? So, and then one can understand a little bit from the microscopic point of view why this should happen, but there are a lot of things which are either confusing or not completely satisfactory. So let's try to understand the statement first, okay? And then we'll see. So it says we cannot take heat from a source at constant temperature. So let's take a source at constant temperature. Let's do an isothermal expansion. Okay? So we take let's take a perfect gas. Okay. So we take, so the temperature here is T1, okay, and we get some heat Q1. Okay. Sorry, this is V, not W. Our system performs work. Okay. Between point A and point B, what is the difference in internal energy? Why is it 0? For a perfect gas. Okay? So the change UB minus UA, first of all, this change is Q1 minus W, right? Because it's the heat absorbed minus the work done. And we say that this is 0, because for a perfect gas, this is only a function of temperature. So we have Q1 is equal to W. So we get heat from a source at constant temperature, and we transform it completely into work. So am I violating the second law of thermodynamics? Why not?
That's the law that says that it's not possible to transform water into work.
Yes, but I have just done it. The law says an extra thing. A cyclic process. Well, here it doesn't ever say cycle, right? It says, that's why I was going to read it and not to say it in my words, because I wanted to use the wording in Fermi's book, which is quite good. So a transformation whose only final result is to transform into work heat extracted from a source which is at the same temperature throughout is impossible. Only the same it is the same temperature. The temperature is constant. We get work out. We get all the heat from the source is transformed into work. But it's not the only result, right? There is also another result. The gas has expanded. The gas volume went from VA to VB. Okay? So the work that we get is not the only result. If we can find a cycle in which, so a cycle, everything has to go back to the starting point. Volume, pressure, temperature of the everything. Except that we took heat from a gigantic source at fixed temperature and we transformed it into work. Okay? If we could do this, then we would violate the second law of thermodynamics. Okay. So here, this is a cycle, right? And we take some work from Q1 and we transform it into, some heat from Q1 and we transform it into work. But why are not we violating here the second law of thermodynamics? No. We said we take heat from Q1 and we transform it into work. It is cyclic, look. It's a closed polygon. It is? The process is reversible, but the law doesn't say anything about the process not being reversible. What's the ingredient here that it's not present in what I read there? We need to.
Okay, at T1, okay, we do work. Okay. I mean, we gave for the system.
You do work, you mean here? Where do you do work? In this cycle, where do you do work? Do you work on the first branch, on the second branch, the third branch, or the fourth branch?
Okay, the system do, okay, the environment do a work on the system, on the first was T1.
No, the system does work. Work is positive.
Okay, yeah.
Here.
Okay, yeah, sure.
So what's Hmm? No, 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 no. It's not about the ideal gas. I mean, the thing, you can get things which are very close to being ideal gases, but it's not because of that. Even if you do this thing with a real gas. Okay. Because the law says we cannot take work from one source and transform it completely into heat. Sorry. You cannot take heat from one source and transform it completely into work. Is every calorie which is taken from source 1 transformed into work in this cycle? No, because we are giving some heat to source 2. Here, we give heat. So heat is given to the system from source Q1, and part of it is transferred to source 2. Q2 is negative. If Q2 were 0, this will be 1, right? Because it will be Q1 plus 0 divided by Q1. Q2 is negative. So here we are not just taking heat from source Q1 and transforming it into work. Some of the heat we can transform it into work. Some of the heat goes out to source 2. Okay, so this is important. Okay, the two important things that you have to remember is that when you talk about the second law is that the process has to be cyclic. So no change except for transformation of heat into work has to occur. And 2, all the heat which is taken from one source has to be transformed into work. If you transform only 80%, that's not a violation of the second law. Okay? Something needs to be lost. Yes?
Okay, can you read it on twice more?
Should I read it again?
Yes.
Okay. So a transformation whose only final result is to transform into work heat extracted from a source, one source, which is at the same temperature throughout, is impossible. Okay? So there is one source, cyclic transformation, and all the heat has to go into work. So before you come to my office and say, oh, I found a cycle that violates the second law of thermodynamics, make sure that you have checked all these things. Okay. There are other statements, equivalent statements of the second law of thermodynamics. And if you go on Fermi's book, you will see he proves that they are actually equivalent. I mean, given one, you can prove the other, and in a chain of implications that goes back to the beginning. So, for example, an equivalent postulate of the second law is that a transformation whose only final result is to transfer heat from a body at a given temperature to a body at a higher temperature is impossible. Okay? So it says that there is no thermodynamic cycle whose only result is to take heat from a body which is cool and give it to a body which is hot. So why do refrigerators work? If you turn off the electricity, the refrigerator doesn't work anymore. You can do some. You can, in principle, take it. Refrigerators don't work on Carnot cycles. Okay, they work on something else. But in principle, if you reverse this cycle, you put some work in, you take some heat from source 2, which is at a lower temperature, you give it some heat to source 1. But you have to do some work. Okay? All right, and is this clear? Okay, so stated in this way, the second law of thermodynamics is pretty intuitive, right? Because we never see such things, transferring heat from something colder to something hotter. We have never seen it happen spontaneously. Like spontaneously means that we did not have to do any work to have it happen. Otherwise, there will be very, refrigerators that work without need. Carnot's engine is also very important because one can prove, but I'm not going to do it. You can still read it on the book, as I said. You can prove that if you have a cycle which operates within two sources, okay, one at temperature T1 and one at temperature T2, Carnot cycle is the most efficient. It's the one which has the highest efficiency. Efficiency is the ratio of the work done divided by the heat absorbed. Okay. And third thing is that every reversible cycle will have the same efficiency as Carnot cycle. And in fact, I don't want to go too deep into this question, but this relation is actually, let me write it like this, 1 minus Q2, the absolute value of Q2, which is, Q2 is negative. So if you now remove the ones, this allows for a definition, for a specific definition of temperature, of a temperature scale, except for a constant, for an overall constant. And the overall constant in the international systems of uni is used to ensure that the number of degrees between the freezing point and boiling point of water is 100. Okay, that's the only freedom that we have. Okay. Okay, now let's look at this expression. And so we have only Q1 divided by T1 and Q2 divided by T2. But these what are they called? These branches of the process here, they are adiabatic, which means that the heat exchange is 0. Okay, so I could also write plus 0 plus 0. So 0 from here and 0 from here. Okay. So I could do something like this. I could write this as the sum of the heat exchanged over all the branches divided by the temperature at that branch. The temperature changes along this branch. The temperature is constant along this branch. It changes along this branch, but changes on this branch and this branch. Okay, because we proved that on the adiabatic expansion, t times v to the gamma minus 1 was equal to a constant, right? So temperature changes since the volume changes. So on this branch, you have to you have to break it in small pieces and some, if you have enough small pieces, and essentially you are doing an integral. Okay? So essentially, we find that for Carnot cycles, this is 0. Okay? Which, let me write it as a you know this symbol? You know this symbol? This is the integral on a closed circuit. When you do integrals when you do line integrals, so integrals in two-dimensional space, it depends. Usually, when you integrate a differential, it depends on the path that you are integrating the differential, unless the differential is an exact differential. And if it is an exact differential, when you integrate out over, when you integrate an exact differential on a closed path, you get 0. Right? Okay, so one can prove that the statement that I gave you before for the second law, yes? dq is not an exact differential. In fact, I should put a bar. Thank you. Yes. dq is not an exact differential. So some books use the notation, they put a bar on it. And we should, since we did it last time, we should actually do it this time as well. Sorry, what was I saying? Okay, so, right, the statement. So this is an observation about the Carnot cycle, okay? But one can prove the following thing. For any cycle, this integral is larger or equal than 0. For any reversible cycle, this integral is equal to 0. So it's not just by chance that we find this for Carnot cycle, because Carnot cycle is reversible. You see, we have drawn lines. It means that the system passed through equilibrium state, and the cycle was done very, very slowly. Okay? The transformation was performed very, very slowly. Since the integral over a closed circuit of this dq divided by t is 0, and the cycle is reversible, so if I do something like this, from point A back to point A, let's assume we are talking about a gas, even not an ideal gas, okay? This. Okay, this might actually depend on the convention, because I think on Fermi's book this is negative. Okay, thank you. It depends on because he has a different convention. Actually, I mean, this last line follows from this line, because since the cycle is reversible, if the cycle is reversible, you can reverse it, and the dq changes sign. So this becomes minus dq. So this integral means it's both less or equal than 0 and greater or equal than 0. It means that it is equal to 0. So the important observation is this one. This follows just with a single line. If you assume that the cycle is reversible. The cycle is irreversible? No. Okay, okay, so let's take a reversible cycle. This means that this integral is equal to 0. Let's take any point B on the cycle. It means that the integral between A and B of dq divided by t plus the integral between B and A of dq divided by t is equal to 0. Now, if we reverse only the second part here, the heat exchange and the work done change sign. The temperature does not change sign. Right? The temperature. So this becomes, let me write this, the integral on from A to B along path 1. So let me write it like this. Path 1, A to B, minus the integral path 2 from A to B. This is 1 and this is 2. This is equal to 0. So this means that these integrals are the same. This means that dq over t is an exact differential, which we call, so it's a differential of a state function, which we call S entropy. If the integral, so let me repeat this. If it doesn't matter which path I take to go from A to B, the integral is always the same. It means that there is a primitive function, right? Such that I can write the integral as the difference of the primitive function at point B and at point A. So this equal to 0 means that this is equal to this, and this is equal to SB minus SA. So dq is not an exact differential, but if you divide it by the temperature T, it becomes an exact differential.
So S is a state function.
Yes.
But it's not dependent by the way.
That's the definition of state function. It depends only on the state where you are. So there is a meaning to saying just the entropy at point B, the entropy at point A. And the difference between the two is given by the integrals. If you know the S entropy at point A, you just take any path you want, this, for example, or this, or straight one, and do the integral of dq for this path divided by t for this path, and you find S at P. Okay. As always, when you have primitives, you know, functions which are defined as integrals of some other functions, then the function is defined except for an overall constant, right? If I have two functions, S and S prime, which satisfy this thing, if I have a function S which satisfies this relation, that's the integral is SB minus SA, if I just add the constant K, in the difference it goes away. The question is,
Is it possible for the entropy of the system to decrease?
so the question is whether it's possible for the entropy of a system to decrease. The answer is, for thermodynamic systems, it is impossible. This is the second law of thermodynamics.
Okay, so the first integral.
Uh-huh.
If we define this integral as the entropy, and it's negative, so
This is not the, this is, this has to be, you have, the entropy is defined as this integral on a reversible cycle, not for an irreversible cycle. Okay?
What I think is not a state function.
Yeah, if you do that integral for an irreversible cycle, you don't get the state function. It's important that you do the integral on a reversible cycle. Yeah.
Okay, why they named it this X entropy? Does that any meaning beside the name, just name, entropy?
Entropy comes from the Greek and means something like inside out. And, something, I don't remember. It's not as straightforward. The name, we can look this up. I mean, you can look this up on Wikipedia and we can discuss it this next lecture. I think it means, entro means inside. So entropy means something like inside out.
Because I mean, usually they name it just with a meaning. So
Yes, no, there is a meaning in the name. I mean, it's not, no, it wasn't just a random name, but there was a meaning in the name. It's the, but I found it only cited once on a book, I think on a book by Epstein, but it's not, the meaning is not explained on any other book as far as I remember. But I'm sure that if we look online, we'll find the etymology of entropy. Okay, so let's calculate the entropy for an ideal gas. So let's take point A and point B. So let's assume that at point A there is volume VA and temperature T, and at point B there is volume VB and same temperature T. Okay? Then, as I said, the integral will not depend on the path that we choose. But if the initial and final point have the same temperature, the most convenient path is straight line? No. Isotherm. Isotherm. Okay? Isotherm. It's same temperature, right? If you take a straight line, then you have to calculate. Actually, why don't you do it as an exercise? Show that show that if you take a straight line, the integral is the same. Okay? So, but now we're going to take an isotherm. Why? Because for an isotherm, du is equal to 0. Okay? So we can get dq by the work done, which is P dV. If the temperature is not constant, then you have a change in du, which is equal to CV dt. Very good. Okay, so we have to integrate between A and B dq divided by t. Okay, so this is the integral between A and B of P dV divided by t. Now, since the cycle is reversible, we can use the equation of state for every point. And we get t as you get t from here, we put it in here, we get that the pressure goes away. And this is n kb logarithm of VB divided by VA. So this is SB minus SA.
Yeah, I remember since the beginning we are working just in this system PV. We can also work PT or P or VT.
Yes.
PV or PT.
And you have a transformation of your system, right? You have three independent variables at the beginning, PV and T. If the transformation is reversible, they are linked by the equation of state. So you have two independent variables. They could be PV, PT, or TV. So you could do the same plot in PT, for example. But PT, you will just see something like this. Because the temperature is constant. And the pressure changes from PA to PB. Okay? But why we do this in this case? Because it's because we want, V is changing and the work is PdV, so it's easier to see that the work is the area under here. In the PT plane, the work is not the area. Right? It's not the integral in P dt. You have to get the volume change when you change the temperature, when you change the pressure, and then you integrate that. So this is the most convenient diagram. But of course, you can do a calculation in any other diagram you want. I mean, you have to do an integral anyway. You can represent it as the area in this diagram. In other diagrams, there is a curve, but the work is not the area. Okay? So, so SB is equal to a constant plus NKB logarithm of VB and this constant cannot depend on the volume, but what can it depend on? Temperature. Why? No, but why in doing this integral we get a constant that can depend on the temperature but not on the volume? Because we keep the temperature constant. Okay? So temperature is a constant, and any constant, the additive constant can actually depend on the temperature. Okay, now we have to get the, so we have the part of the entropy which depends on the volume, and then we have a part of the entropy which does not depend on the volume but depends on the on the temperature. Okay. And so well, it's you see, if you do SB minus SA, you get VB over VA because you get the difference of the logarithms, that it becomes the logarithm of the ratio, right? But if you want only SB from here, this is a constant, and then you have NKB times logarithm of VB. In fact, try. If you get this form of SB, calculate SB minus SA, you'll see that this constant drops out because it does not depend on the volume, And this becomes nkb logarithm of vb divided by vf. Okay? So if we want the part of the entropy which only depends on the temperature, not on the volume, which path can we use? The question is, if we want this constant now, which depends on the temperature, okay, but not on the volume, we want to get the value of this, the dependence on T of this constant. Okay? Say it again. Yes. We integrate now. We take a transformation between A and another point B, C, let's call it C, okay, such that the volume is constant. Okay? So now, SC minus SA, again, will be the integral dq divided by T between A and C. But now dq is what? dw is 0, but du is not 0 anymore. Du will be this. So this will be dq. Okay? And so we put here Cv dt over T. And this is Cv log of Tc divided by T. Okay? For the same reasoning, then we have now the temperature dependence, which will be Cv log of T. In this case, since we are calculating SB, we put log of TB. And then we have a constant now, which does not depend either on the volume nor on the temperature. Okay? Now, we could have done everything in just one step. Okay, let me just pause for a second and let you digest this thing.
We need to reflect between A and B, but we should also find CB, no? If you take this.
Yeah, no. That's what I want to show you now. I just wanted to show you that the dependence on the constant is just, it's logarithmic on the temperature. If one could actually do an integral between any point, so let's take point D, which is here, okay, and does not have the same temperature as point A, it does not have the same volume. Then we have to find the path between A and D, and then integrate. So let me show you how to do this. So since du is equal to dq minus dw, okay, then dq is equal to du plus dw, and so it's cv dt plus pdv. So take any path you want between A and D and integrate cv dt plus p dv divided by t. Okay. And this will give you CV log of TD divided by TA plus NKB log of VD divided by VA. The path can be as following. Can be broken in two pieces. One piece is you go down from A to the temperature of D here. Okay, so there is a path that goes like this. And then you follow an isotherm up to D. And then you see that you, in the first, during the first path, on the first part of the path, this thing is 0, you only have to integrate this and you get the logarithm. On the second part of the path, dt is 0, and here for p you use the state equation of state, and then you get an kb log. Okay? So the entropy of a gas is these only containing the T plus NKB log V plus a constant. And this time the constant does not depend on temperature and the volume anymore. So, since this is a class on statistical mechanics, let's see entropy, the interpretation of entropy in terms of statistical mechanics. Okay? So, first of all, the entropy is an additive function. Okay? If we just, it's additive, it's like the energy. If you take 2 copies of the system, the entropy is just twice as much. Okay. So if I have 2 copies of the system, 2 completely independent copies of the system, S12 is equal to S1 plus S2. So Boltzmann's idea was to interpret the entropy, to link the entropy to a peculiar concept, which is the number of dynamical or microscopic states which are compatible with the given thermodynamic state. Okay, so imagine for a second, from the thermodynamic point of view, in the air in this room, nothing much is happening. Okay? More or less the temperature is constant, the volume is constant. Okay, if you forget that we are breathing, you are changing the quantity of oxygen in it, increasing the carbon dioxide, then and water also. So forget, if this room was completely empty, then nothing will change much. But at a microscopic level, a lot of things are happening, right? Because you have, now we know that there are molecules that fly around at very high speed, they collide with each other, they hit on the wall, there are chemical reactions, whatever. Okay, so there is a lot happening. So there is a number of microscopic states which is consistent with the thermodynamic state, which is constant. Okay, it's not changing. So if you call these states P, the number of these states P you can link it to a probability if you want. If you divide this number of states by the total possible number of states of the molecules in the room, then you see that if you have two independent systems, the number of states of the two independent systems must be the product of the number of states in one system and in the other. Okay? If, you know, my left hand can have 5 possible states, 1, 2, 3, 4, 5, and my right hand can have 5 possible states. If I put them together, they can have 25 possible states. Right? 1 here, 1 here, 1 here, 2 here, blah, blah, blah. Okay? So P12 is P1 times P2. Okay. So, which function does the trick? Which function goes from products to sums? The logarithm, right? And in fact, you can also prove that it's the only function that does this. Okay, let's actually, so this intuitively tell, one solution to this equation, if S has to be a function of P, you would say that S of P is a logarithm, right? But any logarithm works, like base 2, base 10, base 20, base 107, whatever. And all the logarithms, and essentially what I'm saying is that I'm changing the constant in front of the logarithm. And since it was Boltzmann's idea to look at this thing, the constant which is in front of the logarithm is called Boltzmann's constant.
I'm not understood how you. Okay, what is the probability you are talking about?
Right. So let me repeat what is this probability. We will see it in the second part of the class. So I just want to introduce the concept now and keep you interested until July, when we will talk about exactly this thing. So for the moment, is the following thing. So there are many microscopic states of the molecules in an object. For example, in the air in this room, which are consistent with macroscopic or thermodynamic observables. Right? They have the same pressure, they have the same entropy, they have the same internal energy, they have the same temperature, and so on and so forth. The same volume, and so on and so forth. So you can count them, sort of, okay? In order to count them, you have to be careful, because these are, the position of the particles are continuous variables. So, but forget for a second that they are continuous variables. Suppose they are discrete variables. So then you can count the number of states which are compatible with given pressure, given temperature, given volume. This is P. It's that number. Okay? Very simple. I should call N. I should have called it N, but N is the number of particles. So, So Fermi calls it pi. But pi for us is 3.14, 15. Blah, blah.
Is it always a product P12?
If they are independent, if the two systems are completely independent, then it's a product. Okay? Okay. So the entropy, this is something that we will use a lot in the second part of the class, but for the moment, for thermodynamics, this thing is absolutely not necessary. So I'm giving it to you as a teaser of what we are going to see in the second part of the class, which is connection between microscopic world and thermodynamic world. It's not what? Oh, macroscopic is when we, I mean, in a statistical mechanics class, macroscopic is thermodynamic. I mean, when you take a lot of systems, you always take the thermodynamic limit, which means that you take a lot of systems and a lot of energy, okay, in such a way that you can talk about temperature. If you take a lot of systems at rest, then you, or with very, very small energy, then you end up in something which has zero temperature.
Is there a limit, a thermodynamic limit on T, number of particles?
The number of states, you mean? There is not a limit, but because it grows. A limit means that something goes to, right, goes to
Microscopic system to microscopic system.
from a microscopic system. So the question is, what is the limit of P from microscopic to macroscopic system? What I can tell you is that P grows very fast, exponentially fast, okay, with the number of particles. And this you can already see, because if your particles are completely independent, you have to take P1 times P2 times P3 times P4, blah, blah, blah. Okay. If you consider, you know, your particle, in the extreme case in which your subsystem is one particle, for which, you know, this doesn't really work. But let's assume we could do it. Then you would already see that in order to get n particles, the number of states of n particles, then you have to multiply it n times. So this thing grows exponentially. And in fact, the entropy, which is the logarithm of P, is something which is of order n, you see? See here. So the entropy is something which is of order n, so this means that P is something which is exponential in n. Okay, so let's now use the fact that P is a state function. Let's see what we can get out of it, okay? Did I say P? Oh, I meant S. The entropy is. So, dq over t is a state function. Is an exact differential, okay? And as we said, dq is du plus p dv. Now, let's consider not just ideal gases, but general systems, or general gases, okay? Then we don't know that du is Cv times dt. It could be anything. For example, for a non-ideal gas like van der Waals gas, du depends on the volume as well, okay? So let me write this as, so du will be equal to du in dt at constant volume times dt plus du in dv at constant temperature times dv. And if I put this in,
For the last result, can we say that we cannot found a system without states?
from the last result, can we say?
S equal kb logarithm of p.
Uh-huh.
Can we say that we cannot find system without states?
Yeah, but I think that's intuitive, right? A system has to have at least one state, otherwise, yeah. In that case, the entropy is 0. And actually, that's important. But the logarithm of 1 is 0, right?
No, if we have not
The minimum number of states of a system is 1, it's not 0. Okay. Your system can at least have one state. And the entropy is 0 for that system. Okay? And this actually, we will see that it's actually related to the third law of thermodynamics, which was added much later. And it's that, and we will see about it either today or tomorrow. Okay. What did I want to do? Okay, so from this thing here, dq is equal to du, let me write my u as a proper u, in dt times dt, constant volume, plus du in dv at constant temperature plus p, everything times dv. So entropy is equal to 1 over t du in dt at constant volume times dt plus 1 over t du in dv at constant temperature plus p times dv. Okay? So this part here is ds in dt at constant volume. This part here is ds in dv at constant temperature. S is a function of p of t and v. S is a function of p, v, and t, but p, v, and t are connected by the equation of state, which we don't know what it is, by the way, because we are talking about non-ideal gases in general, any gas you want. But this thing has to be equal. This equality is true for any gas. So what happens if I take the derivative of this with respect to the volume and the derivative of this with respect to the temperature? They should be the same. Because if I have a function of two variables and I want to take the x and y, and I take the derivative with respect to x and then the derivative with respect to y, or vice versa, I take the derivative with respect to y and the derivative with respect to x, it doesn't matter.
But the thing is not always true, right? I mean, sometimes they don't commute.
No, for exact differentials, they do. That's right. If that is not true, then it means that you can make a small loop and get something which is not zero. Right? Right? And this means that the integral on a path is not zero. But we are saying that this is an exact differential. So this is true for these functions. For example, it's not true when you have fields, when you have vector fields, like the magnetic field, which is a rotor. Okay, in that case, it's that's not true. Okay, so if I take d by dv of 1 over t du by dt, this has to be equal to d by dt of 1 over t du by dv plus 1 over t times p. Okay, so this is 1 over t d square. So the first term is d square u in dt dv. And the second term is d by dt 1 over t du in dv plus d by dt 1 over t times p. Okay. Now this term here is equal to 1 over t d square u in dv dt. And then we have the other term, which is minus 1 over t squared, which is the derivative of 1 over t, du in dv. And then we have, this term is left invariant, d in dt, p over t. But look, this term and this term are equal, right? So we have that these two terms sum to 0. So we have that d by dt p over t is equal to 1 over t squared du by dv at constant temperature. These sorts of equations are called Maxwell's relations. You can have fun. You can find like 20 of them. If you write S as a function of T and V, you can change variables and you can use P and V, and or you know, T and P, and you can use the internal energy instead. You can use, you know, there is essentially an entire chapter on Landau Lifshitz book, which can be called Fun with Maxwell relations, because it finds like 20 of them. And derivatives of specific heat are connected to each other. But this one here, I'm proposing it as an example because it's very powerful, actually. Suppose that you have a substance like a gas, okay, in which you do an experiment and you find that at constant volume the pressure is exactly proportional to the temperature. You do an experiment, you find some points, and they follow more or less a straight line. Okay? Then it means that P over T is a constant. So d by dt of P over T is 0. So this means that the internal energy does not depend on the volume. Okay? So, but remember, we had to use this. We are using a lot of things here. We are using the fact that we are using the first law, okay, because we wrote du as dq minus dw. We are using the second law, which says that ds is a state function. Okay, so we are using a lot of things. So it's not just for free. So if P over T is a constant, independent on the temperature, it can depend on the volume. Okay, I'm not saying that it does not depend on the volume, but for fixed volume is a constant. Then, and actually the opposite direction is also true, the internal energy at constant temperature is independent of the volume. Okay, so this tells us something. So first of all, tells us that for an ideal gas, this is true, because P over T, PV is equal to N kBT, right? So P over T is N kB is divided by V, which is independent on temperature at constant volume. And in fact, for real gases, for ideal gases, we have that U is only a function of the temperature, not of the volume. U of TV is CV times T for real gas. It could have been some, I mean, this is not so powerful to tell you that it's linear in T. It could have been T squared, T cubed. But it is powerful enough to tell you that there is no volume dependence at constant temperature. You always have to say, I mean, it's a bit of a hassle, but you always have to say at constant temperature, at constant volume, because since volume and temperature are connected by the equation of state, you always have to specify which are your variables, the variables with the independent variable, temperature, volume, and pressure are connected by the equation of state. You always have to say if your independent variables are P and T. So in that case, you say at constant temperature as a function of the pressure, or V and T. In that case, you say at constant temperature as a function of the volume, or at constant volume as a function of the temperature. You have to be careful. This is something that we are going to discuss. For example, there is van der Waals equation of state, okay, which relates, in which you have P. Actually, let me give you a precise form. So with the correct name of the coefficients, yes. So it's P plus A divided by V squared times V minus B is equal to N kBT. This is van der Waals equation of state. Okay. Actually, you could use this equation to find the temperature dependence of, to find the volume dependence of the van der Waals, of the internal energy of the van der Waals gas. If you just, write P divided by T here, and this is some function of V. Take the derivative and blah, blah.
Are they constant, A and B?
Yeah, for a specific gas, they are constant. We will talk about this. Okay, so the last thing that I want to tell you, and then we'll take it back tomorrow. Actually, if you, for any real gas, when you lower the temperature, this thing starts deviating. Okay, the pressure, I think when you lower the temperature, actually from here you can see it. At constant volume, Yeah, constant volume, this goes to, does not go to 0, but goes to a constant. Well, okay. Is it true? No, P over T. P is linear in T, but P over T is not a constant because P will be equal to NKB T divided by V minus B, and then there is a minus A over V squared. Okay? So P over T and actually, so this actually deviates from below. Okay. The last thing I want to tell you is about the third law of thermodynamics. The third law of thermodynamics tells us that so S is defined as except for a constant, right? For any system, not only for real gases, for any system, because it's an integral. We only define it to saying the integral between A and B does not depend on the path. So, but how did you get to A? Then you have to take another point, and so on and so forth. So there is a freedom of choice of a constant. The third law says, it seems very innocuous, but it's not. It says that the constant can be chosen such that the entropy at 0 temperature is equal to 0. Okay? Which in the statistical mechanics interpretation means that how many states are there at t equals 0? 1. Right? Okay. Says that the constant can be chosen such that S of t equals 0 is equal to 0. Okay, this doesn't seem like a big change, right? A big event. I mean, it's a constant. But if you think for a second, S of t is the integral between, so S of t minus S of t0 is the integral between t0 and t of dq divided by t. But dq is the, suppose we do a change, it depends on our path, right? So suppose we do a change, we follow a path at constant pressure, then dq would be Cp times dt, where Cp is the specific heat at constant temperature, constant pressure. Sorry, it's the definition. It's just the definition. The same thing if we follow a path of constant volume, instead of Cp we get Cv. So whatever, specific heat. And since the third law says that if we put T0 is equal to 0, then this thing here is 0. Let's put T is equal to 0. And so this goes to 0. So let's consider, for example, perfect gases. Okay? So for a perfect gas, ideal gas, monoatomic, Cv is a constant. It's 3/2 times nkb. And what's wrong with this equation then? The integral diverges. Right? So this cannot be. So what's wrong? The perfect gas or the third law of thermodynamics? In this case, the perfect gas is actually what's failing. Okay? in fact, CV is not. In fact, first of all, there are no perfect gases at 0 temperature. If you take any gas, there are no gases at 0 temperature. If you take any gas, you decrease the temperature, it liquefies and then solidifies. Okay, it becomes a crystal. But also a crystal has a specific heat, right? Crystal like, I don't know, iron, aluminium, whatever, a metal, has a specific heat. And the third law says that also that specific heat has to go to 0, at 0 temperature. Okay. So any system, although for large temperature the specific heat can be constant, it has to go to 0 when the temperature goes to 0. This is quite powerful, I think, as a prediction. Also because classical mechanics does not give this prediction. For if you don't introduce quantum mechanics in the game, the specific heat remains a constant up to arbitrarily small temperatures. It's only quantum mechanics that makes the system go in one state, which is called the ground state. In classical mechanics, you can have different microscopic states of your system which are compatible at any low temperature. But for quantum mechanics, when you go to 0 temperature, only one state wins, and that's the ground state. Okay. The last question, if anybody knows. What's the specific heat at constant pressure for a crystal at large temperature? 3 half? No, that's I'm talking about a crystal. So for example, you say 3 half. It's 3 times R. Ah, okay, sorry. I thought you said 3 halves. 3 R. Why 3? So for an ideal gas, is 3 half times R, right? Yeah, it has to do with degrees of freedom. It's the equipartition of energy gives that. Okay, very good. Okay, but that's correct. 3 R. Okay, it's 3 R and then goes. Then when you reach a certain temperature, it starts going down. This temperature is called Debye temperature. It's usually indicated by a capital theta. Okay, let me stop here because our time is up, and I will see you tomorrow morning.